Good afternoon, everyone. My name is Denis Shilin. I am a researcher of Federal Scientific Agroengineering Center VIM. Today, I would like to talk with you about automated control systems in agriculture. My aim for today's presentation is to give you information about research on the kinematic model of a coal milking manipulator with simultaneous positioning at 4 given points. Industrial robots are widely used in manufacturing and in science. As a rule, industrial robots are represented by automatic programmable manipulators that perform complex operations of special moving. These robots are used in hazardous or high-precision manufacturing. They are used in light and heavy industry, and the list of robotic systems used in agriculture has been recently expanding. For example, large dairy farming companies are really using milking robots, self-propelled robots for distributing and transporting feeds. The most technologically advanced solutions are milking robots, as they perform a number of operations such as locating at the teats, they pre-cleaning with process or washing in the milking cup, feeding, weaning an animal, one by one fitting teats cup over cow's teats, individual milking each quarter of the udder, assessing qualitative indicators of milk, and successive disengaging teat cups. This robotic system contributes to complete replacement of human labor and improved product quality, as well as ensures preventive protection against teat disease resulting from dry milking. The most expensive and complex part of the milking robot is the system for manipulation, the walking units, and a feedback system for special orientation required for manipulations. But even if this part is the most complex and expensive, it doesn't provide the maximum completeness of milking, since the cup are connected to the teats in turn, which weakens the response to the irritation phase of the teat receptors to stimulate the maximum return to alveolar milk, which reduce complete emptying of the alveoli. Delays during the attachment of teat cups also reduce the ability of fully utilize the neurohumoral phase of milk transfer, since oxytocin is secreted only once and enters the udder from 35 to 50 seconds after the first teat has been stimulated. By this time, exciting milking robots are only finishing fitting the last teat cup over the teat still containing a portion of system milk. So, the goal of the work is to solve the problem of the kinematics of the manipulator intended for automatic servicing of livestock. The arm of the manipulator is a system that positions all 4 teat cups to the individual teat position. A significant advantage of this manipulator kinematics is the ability to simultaneously connect milking cups to the teats of a cow's udder to provide physiologically more correct milking and reduce the total milking time. To solve the problem of simultaneous fitting teat cups over cow's teats, we have developed a robotics manipulator shown in this slide. The design presented above was developed based on the kinematics of the previously designed manipulator in our laboratory, supplemented with a model that provides the ability to control milking cups in a horizontal plane shown in this slide in the right. The core difficulty of finding a solution to kinematic problems lies in the manipulator links, which are located in the 0xy plane, the kinematic diagram of which is shown in this slide. The direct kinematic problem involves finding the position coordinates of the working units. The kinematic diagram of the working units are indicated by points K, L, M, and N. To find a solution to the direct kinematic problem, a system of equations was drawn up. presented on this slide. The inverse kinematic problem involves finding the angles alpha 1, alpha 2, alpha 3, and alpha 4 at distance s1, s2, s3, s4, and s5 from known position points k, l, m, and n. Numerous solutions of the inverse kinematic problem are possible, which must be limited by boundary conditions. This slide presents a system of equations that analytically describe the kinematic diagram and is designed to find a unique solution in accordance with the specified boundary conditions. To verify the direct and inverse kinematics problems, studies on boundary conditions were carried out. With alpha 1 equals pi share 2, alpha 2 equals pi, alpha 3 equals alpha 4 equals 0, the manipulator will walk along the abscissa axis along in its entire length equal to the total length of all links L1 plus L2 plus L3. This slide shows a graphical representation of a manipulator in a plane. So, with alpha 1 equals 0, alpha 2 equals pi, and alpha 3 equals alpha 4 equals 0, the manipulator will walk along the ordinate along its entire length equal to the total length of all links L1 plus L2 plus L3. This slide also shows a graphical representation of manipulator in this plane. With alpha 1 equals 0, alpha 2 equals pi share 2, and alpha 3 equals alpha 4 equals 0, the manipulator will walk along the ordinate to the length L1 and along the abscissa to the length L2 plus L3. This slide also shows the graphical representation of a manipulator in a plane. With alpha 1 equals pi share 4, alpha 2 equals pi, and alpha 3 equals alpha 4 equals 0, the manipulator will operate at an angle for 45 degrees to the abscissa and ordinate axis over its entire length equal to the total length of all links L1 plus L2 plus L3. This slide also shows its graphical representation of a manipulator in a plane. Many solutions of the direct kinematic problem represent the reachable zone of each working block shown on this slide. So, its top view, blue line is manipulator, green points is working body reachable area, and black points is other point cloud. So, at the end of my report, I'd like to note the following. The study has offered solutions to the direct and inverse kinematic problems. When solving the inverse kinematic problem by the Newton method to achieve a correction of 0.001 meter, the number of approximations didn't exceed 10. The obtained reachability zone of the manipulator is symmetrical with respect to the second link. The issues discussed in this paper will significantly simplify the search of control algorithms of the manipulator of the Milken unit. With the help of the developed program, it's possible to study the kinematics of similar design schemes with various dimensions. This concludes my presentation. Thanks for attention.